So your textbook has a pretty good synopsis of all these different devices that we might have for network security. It talks about firewalls and routers and things like that. What I wanted to do in this unit is rather than just going through all these different devices, I wanted to give you a little primer on network security and some of the underlying standards and protocols, because I think it's important to understand those under the hood a little bit, to understand what the ramifications are or how network security devices work. So you really have to understand networking to really understand network security and how these network security devices work and what's appropriate to use and why we use certain devices, for example, like firewalls and routers and so forth and so on. In any course where we discuss networking, and hopefully you've been exposed to this in previous courses, they always talk about the OSI model. So every textbook beats this to death. They talk about the OSI model. You've probably seen this 1,000 times, but they always talk about these 7 layers. It starts with the application layer, and the basic concept is with the OSI model that you start with the application layer and you pass that information through these different layers, which do different things with the data until it eventually gets to a wire, sent over the wire, and then you sort of de-encapsulate that until you get all the way back up to the application layer. And in IT security, a lot of times we talk about how, from an IT security perspective, the simpler devices, the lower you are in the stack, the simpler it is to the more complex it is to secure that technology. So application layer can get rather complex, whereas the physical layer can be relatively simple from an IT security perspective. But what I will tell you about the OSI layer is it's a conceptual model. Everybody always says it's a conceptual model, but the thing about OSI, it actually is a standard. You can go read about it. It was developed in the late 70s, and it was never really used. It was never really put into practice. There was a competing standard called TCP/IP, which really became the standard. So I don't know why we still teach the OSI model. Well, I shouldn't say that. The reason we still teach the OSI model is because everyone expects everyone to know it for some reason, but it's almost completely useless in IT. And I'll talk about another model. But before I do that, let's talk about just some of the basics of networking. The really, really basics. We go back in time. Old networks, back in the 70s might have been a bus-style network where you had computers sort of daisy-chained together, which was very susceptible to failure. There's some very old technologies that supported that, and hopefully you won't see that in the real world anymore. But later on, to make networks a little less susceptible to error, people started implementing these ring-based networks. Token ring, of course, was the most common from IBM, which was definitely a huge step in networking as far as reliability goes and network performance. But it still wasn't quite, it still had some issues. Certainly, troubleshooting them is a little bit more difficult for sure. But they still exist. They're still out there. You still see some older mainframe type networks that are using token ring. But most modern networks use what we call a star topology, where you've got all the computers sort of interconnect into one central wiring device, which in the old days would have been a hub and today mostly is a switch. And I'll talk about why in just a few minutes. But you have the central wiring device, and that was known as a star topology, or is today known as a star topology. Almost every modern network is a star topology, whether it's a wireless network or a wired network, it doesn't matter. There's always some central device that all the computers connect to. And those centralized devices, the switches, could also be interconnected to other switches through things like routers. Or you can interconnect them even through switch backplanes. So most newer switches, those made in the last 10 years, you can have different switches all connected to a single backplane. So even though you might have switches splattered all over a network in different data closets, they're really all one big switched infrastructure. It's very efficient. Switching is great because if you have one failure of one computer, it doesn't affect anyone else. You could see with the bus and the ring, if you have a failure of a computer, it affects peripheral devices that are peripheral to it. We don't have that as much with a star topology. So one of the big reasons that it's become so ubiquitous. So usually when you have multiple networks separated by a router, we call each one of those networks a LAN or a local area network. And a collection of local area networks typically is a wide area network. So most organizations that are large, that have multiple offices, you might talk about the WAN or the wide area network, or any traffic that's originating from outside our local area network might be considered the WAN. For example, some people consider the internet to be the WAN. But as far as the vernacular goes, it doesn't matter which, whether you're referring to the WAN as my larger area network, outside my local LAN, or if it's the internet, those terms are sort of interchangeable. But I wanted to give you an idea of sort of the background in case you haven't been exposed to it, just so you can see it. In older networks, or not older networks, really in any network where all of our computers are connected to one another and there is nothing that is responsible for authentication and authorization and the things that I talked about in the previous presentation, we call that a peer-to-peer network. But in most modern networks, in most companies, one of these computers or several of these computers are responsible for authentication, or maybe it's a file server offering some kind of services on the network. But anytime we have something responsible for authentication and authorization that other computers rely on, we call that a client-server network. So client-server is what is probably more common in most organizations. Obviously, most of us don't have that at home, but in most networks, you're going to have a client-server network where you've got sort of core services being offered to users on the network, like authentication, authorization, and so forth. And I'm sure you can imagine that if you had a network that did not have some kind of a server that was responsible for authentication and authorization, managing that network would be rather difficult. And I think the number is usually about 10. If you have more than 10 computers and 10 users on a network, not having some authentication service sort of becomes unwieldy at that point. I know 10 doesn't sound like a lot, but if you think about it, if you've got 10 employees in a small company and, one or two of them quits, every once in a while, if you have let's say you had an attrition rate of around 10%, which is pretty darn good for most companies, that means that every year you've got at least, one person that's leaving or coming in. And that means you have to go around and edit the permissions on all 10 computers every single time and hope that you don't miss anything. And that's only 10 computers and 10 users. As you go up, let's say you had 20, 30, 100, once you get to those kinds of numbers, it becomes almost impossible to manage it. Now at a 10 or 15% attrition rate at 100 users, we're talking, 10 or 15 times. That means almost once or twice a month, we're going around to 100 computers to edit permissions. That's a lot of time and effort. It's almost a week and a half of your time every single month. That's 25 to 30% of your time, and that's only 100 users. Imagine if you had 1,000. So most real networks, most corporate networks, most organizational networks, we have a client-server model. All right, so I talked about the OSI model. And I talked about how we don't use it anymore. What we really use is the TCP/IP model. OSI never got implemented. I can't think of a single implementation of the OSI model. I'm sure someone's going to email me and tell me I'm wrong. But I don't know of any implementations of the OSI model. And if there are any, they probably are not used anymore. They probably were implemented in 1979 or 1978 or something. But for the most part, TCP/IP is the de facto standard for networking. Almost everyone uses TCP/IP. There are other standards, and I'll briefly talk about one of the other standards, which is very slowly dying. But TCP/IP is by and large the most common. And one of the things that a lot of textbooks get wrong, that I want to make it clear, a lot of textbooks will tell you that the TCP/IP model is derived from the OSI model, and that is not correct. TCP/IP is its own model. It uses a very similar vernacular and a very similar structure, but it's its own model. And one of the things that they will tell you is that the OSI model is a conceptual model of the TCP/IP model, but the application layer encapsulates the application, presentation, and session layers of the OSI model, and that is not true. TCP/IP does not have a presentation or session layer. There is no such layers in TCP/IP. They do not exist. Those goals of presentation and session are met through the transport layer. So if anything, when they talk about them being consolidated, if I had to say that 6 and 5, layer 6 and 5 in OSI are consolidated into anything, it'd be more consolidated into the transport layer than it would be the application layer, especially session. Now we'll talk about how TCP/IP does that. It's a very simple standard. You can go out and read the RFC. I think it's RFC 793, written by Postel is his last name. I can't remember his first name. It might be Tim Postel. But you can go look up the RFC. It's not that long. It's a pretty easy read, but it'll give you a lot of in-depth understanding of how TCP/IP works. So let's talk about how the standard works. So we start with the application layer. Let's say we had some payload of data that we want to send over a network. Let's say the payload is foo. And at the end of the day, all data is nothing more really than ones and zeros, right? So for the purposes of this course, let's just ignore what the data actually is, and we'll just call it data for simplicity's sake. We don't care what it is. It's just data. We have this random blob of data that we need to get from point A to point B. And again, this is a lot of review of what you might have talked about in a networking class previously. But at the transport layer, we surround the data with a segment header and footer, or we encapsulate, right? So that's called encapsulation. We take our data at the application layer and we encapsulate it at the transport layer with a segment header and footer, which delineates the data that's inside that segment. And then we take that segment, we pass it down to the network layer where it's encapsulated once again with a packet header and footer, which delineates the segment that's inside that packet. And then that gets passed down once more to what's called a frame. And we have a frame header and a frame footer, which again delineates the packet that's inside that frame. And then finally, that whole package is sent over the network, over the physical layer as ones and zeros. It's transmitted over the network as ones and zeros, where we reverse this process by taking the frame and stripping off the frame header and footer. And we strip that off to get to the packet layer, and we strip that off to get to the segment layer. Throughout the life cycle of data, as it goes through a network, all of these things are stripped away and put back on depending on the devices that it goes through. I'm going to show you an example of that here in a second. So a frame, for example, is the outermost layer. So that is the layer that is most often stripped and reapplied by devices as it goes through the network. And the layer that's very rarely stripped and reapplied would be the segment layer, which is at the transport layer, which is really TCP. So this idea of encapsulation is really important to understand as far as how networks work. So I wanted to kind of make it clear this concept of encapsulation. So let me talk about the data link layer. Well, first of all, the physical layer is rather simple. Physical layer is the standards for actually moving those ones and zeros over the network. That's our copper, our wireless, what have you, infrared, it doesn't matter. For example, 100 base TX, 100 base F, 100 base T, 10 base T, whatever, 1000 base T, which is probably more common now. Those are all different physical standards. They're all IEEE standards. You can go read about them in the IEEE website. You can go look up all these different standards. You have, of course, access to do that with your Drexel account through the library. But you can go and look at what those all are and what they mean. So the data link layer, let me jump up to the network layer. So there are two protocols really that are common at the network layer. IP layer is the most common, or the Internet Protocol. And that's the one that I'm talking about in this presentation. That's in 99.9% of all networks use the Internet Protocol. The Internet uses the Internet Protocol, so it's the most common. But some networks still use IPX, which is an older Novell standard. I always get one student that emails me and tells me how Novell is the cat's pajamas, and don't knock Novell because it's great. But no matter how much you love Novell, that standard is dying, and it will be gone at some point. It's not going to be common. And it already is not common. I can think of very few networks that are using IPX. So IPX is the other standard. But in the middle here, sort of sandwiched in the middle, are the data link standards. You have 802.3, which is the MAC standard, which I'm going to explain, which can work directly with IPX and IP. And then you have 802.5, which is the token ring standard, which is supported by 802.1x1 for bridging and 802.2 LLC, which can then either go directly to the IP and IPX layer, or if you're using IP, you can do 802.2 snap. I'm not going to talk about token ring in this class. We are not going to learn about it, but I do want you to be aware that it exists. Why do we care about it? Because a lot of older networks that support older mainframe systems sometimes will still use token ring. And a lot of times it's only for that limited scope, but it's important to be aware that it exists and it's still out there. It was an older IBM standard. So mostly what we're going to concentrate on a course like this, just because we want to look at, for the purposes of this course, what's most common, we'll look at the IP layer and 802.3 MAC, which is the data link layer used in TCP/IP, or mostly with TCP/IP. So the data link layer, basically, if you've got a bunch of computers on the network, in the old days, they would all connect to something called a hub. A lot of you have probably heard of a hub. Most of you probably don't use them because they're very old devices that most people have phased out for a variety of reasons. I'll explain why from an IT security perspective. It's a good thing that we phased out hubs. The way the computers communicate at the data link layer. So if you have computers that are all interconnected through a hub, each computer has a MAC address. So it's a unique address that is hard-coded into the device itself. Every computer has one. If you go to your command line in Windows and type ipconfig, you'll see what your MAC address is. It'll look something like that. It has two parts. One part is designates the manufacturer, and the second part, each manufacturer guarantees unique to any device that they create. So if you buy a Netgear network interface, it's going to have Netgear's prefix with a suffix that they guarantee is unique. So you'll never have two devices with the same MAC address. At least in theory, you'll never have two devices with the same MAC address. So if two devices on the network want to communicate, let's say I'm on computer number 1 on the left-hand side. So in my packet or in my frame header, right, because the frame is what we use at the data link layer, I would say that my originating MAC address is A, and I want to send to the computer whose MAC address is 3, which you see on the end on the right-hand side. So if I wanted to send that traffic to number 3, the problem with a hub is I send that data link frame, I send that frame to the hub, and the hub simply repeats that to every computer on the network. It's a dumb device that simply sends that traffic to everyone that's connected to it. And the only thing that prevents number 1 and number 2 from responding to that request is the fact that they don't have that address. So they just ignore it. And then the computer number 3 responds and says, that's me, let's have a conversation. And then we go back and forth talking to each other. But everything we're saying to each other can be listened to by computer number 1 and number 2. If computer number 1 or computer number 2 had some software that just captured all the packets that are received on their network interface card, they could log all that, and we could see all the information being transmitted between computer A and computer number 3 on the other end. Because a hub, again, it's a dumb device. It's just going to repeat everything. It's just a simple electrical device that retransmits every single thing that hits any one of those ports. One of the other disadvantages I'm not going to talk about too much that you probably heard in the networking class is when you use something like a hub, it's not very efficient because you have all this traffic going to every computer and you're ignoring most of that traffic on a larger network. So hubs are kind of limited in scope. You can't have a hub for thousands of computers because you wouldn't have, it'd be like being in a room with 1,000 people all trying to talk at the same time. In a small room, it's manageable, but in a large room, it's not manageable. So, everybody tries to have, you can't have a conversation with somebody on the other side of the room when there's 1,000 people there. They have to be close to you, and, it's difficult to do that. So to fix all that, most networks utilize a switch, which is a little bit smarter. So with a switch, when you send traffic to the switch, to a port on the switch, and again, this could be a physical switch for Ethernet, or this could be a wireless access point, but when the traffic goes to the switch, it's smart enough to know that your destination is 3. So it's coming from A going to 3, and it only creates that electrical connection to 3. Number 1 and number 2 do not see that traffic. They can't listen to that traffic. They don't, as far as they know, that traffic doesn't exist. So it's a private conversation between A and 3, and you can tell that that's definitely more secure than the alternative, without a doubt. One thing I'll mention here, though, is most switches that are in the enterprise, you have the ability to put switch ports into promiscuous mode. Promiscuous mode basically turns that port into a hub so that you can monitor all the traffic. And it's important to be aware that a lot of switches have that capability. And usually it's for troubleshooting, but an attacker could use that port, right? So if they had physical access to the switch and they could go in and plug into a promiscuous port, or if they have the ability to set a port as promiscuous, which can be done in many switches, then you have that original problem with the hub where somebody could listen to all that traffic. But mostly I want you to know what a switch does, why we use it, and basically how it works. It's a very simple device. But now let's switch up to the network layer. So in the network layer, so what you're seeing at the top of my screen right now is the frame, right? So encapsulated within that frame, so let's look at now what's inside that frame. You have a packet, which has a header. A packet header, I didn't show you what a frame header looks like, but a packet header is a little bit more complicated. But the thing that we're most concerned with that I want to talk about in this class is the source IP address and the destination IP address. That's one of the common fields that we're going to use with something like a firewall or a router to block or pass traffic on a network. So most of these internet security devices that they talk about in your book, they look at the source and the destination IP address of a computer. So for example, if you take a look at that packet that I have at the top, the packet header has a source IP of 10.11.12.13 with a destination of 172.20.21.22. So let's talk about IP addresses just very briefly. I'm sure you've seen this in other classes, but just to level set everyone on an IP address and how routers and firewalls understand IP addresses. The thing about the network layer, at the data link layer, everything has to be directly connected to the same switch or the same switch backplane in order to talk to each other. What's nice about the network layer is we can extend beyond switches and go through routers, which can route traffic between different networks. So the network layer with these network layer addressing with an IP address allows you to go outside those boundaries. So you can literally go anywhere in the world as long as there's a path, an electrical path from point A to point B through routers, you can get there. So it's a little bit more complicated, the addressing. Number one, it's not assigned by vendors or manufacturers. It's something that we assign ourselves to our networks and our computers or routers and switches and so forth. Or you're assigned an IP address by an ISP if you're on a public network or a public-facing interface, or an interface facing the internet, I should say, or the WAN. But an IP address contains two parts. Well, first of all, an IP address is a collection of octets. So an IP, and by the way, I'm showing you IPv4 because IPv4 is much simpler to understand. IPv6 is far more complicated. IPv6 is being adopted much more than we thought it would be by now, but it is getting adopted much more. But I'm not going to talk about it in this course because it is a bit complicated, and that's something I would expect that your networking classes would have gone over. But the concepts are the same. The idea is the same. It's just that the implementation of it is much more complicated rather in IP version 6. So in IP version 4, you have a collection of octets. There are 4 octets. An octet is literally a collection of 8 bits. That's all octet means. So an octet is simply 8 bits. So it's 4 sets of 8 bits. So the first number, in this case, 172, you can see the bits, .20, .21, .22. And that's how I would represent that IP address as binary, as a set of 4 octets. There's also a portion of a network address, which is the mask, or what tells you which portion of the address is the network portion. So in IP, or the Internet Protocol, you always have a network portion of an address and a node portion of address. So you identify networks and nodes, sort of like a telephone number. So a telephone number has different parts, for example. So for example, Drexel's telephone number is 215-895, and then 4 digits. But without a doubt, when you see a phone number that's 215-895, that's Drexel, because 215 means it's in Philadelphia, and the 895 is Drexel's exchange. So those 3 numbers in a telephone number are called the exchange, right before the line number. So the last 4 digits is called a line number, which rings a specific phone. Although in some phone systems you also have an extension, which is, we'll talk more about that with port numbers. We can kind of use the same concept. But those different parts of the phone number, mean different things. In an IP address, the first part of the IP address tells you what network it is, while the second part tells you which node it is. What's different about this than a phone number is that in a telephone number, the area code almost always tells you what area the phone number is in. 215, for example, being southeastern Pennsylvania. In IP, that portion of the IP address that denotes the network can always be different. It doesn't always have to be. In this case, it's the first 3 octets. So the first 3 octets tell me that this is that are the network portion of this address, but it doesn't have to be that way. I can use anything as part of the network address. It does have to be the first part of this, and then the second part, the node. But where we delineate that can be on a sliding, sliding back and forth. So the mask at the bottom, the ones tell me that the first 3 octets are the network portion. So I know that 172 is network because it's 11111, right? It's all ones, the 20 and the 21 and so forth. And the 22 I know is node because it's all zeros. So in networking, sometimes we'll call that a /24 subnet, meaning that the first 24 bits are the network portion of the address and the last 8 bits are the node portion of the address. In Windows, you'll usually see that as 255.255.255.0. If I wanted to, I could use the first 22 bits for the network portion of the address. So I can borrow some of the network portion to use in the node portion. So now my network is the first 22 bits, not the first 24 bits. So then it goes from being a /24 to a /22. And if I were putting this in Windows, instead of being 255, it would be 252 because the binary equivalent of 11111100 is 252. So again, I just wanted you to be familiar with IP addresses and how we know the difference between, how we know that one is on one network and one is on a different network. In this case, it's pretty obvious because the source IP address in this packet is 10.11.12.13, and the destination is 172.20.21.22. So clearly they must be on different networks. Now, I talked about how a switch can only send traffic between computers within the same local area network. We need a router to go between those two if we want to go outside the local area network. So switches work on MAC address, and routers, because they're networking devices, work on IP addresses because they're internet protocol devices. They work on the IP address. So if I have a computer on the left, which is 12.13, that computer wants to communicate with the computer all the way on the right, which is 21.22. So my computer at the switch layer, the only thing the switch understands is MAC addresses. So the first thing my computer has to do is if I know I want to get traffic to 172.20.21.22, my computer doesn't know how to get to 172.20.21.22. It doesn't know what network that's on. It doesn't know how to get there. It's not a router. It's not its job to know. Just like when I put a letter in the mailbox, I don't know how it gets to Drexel University when I put it in my mailbox. All I know is that it gets there. The Postal Service handles everything in between. But as long as I have it addressed the right way, it's going to get there. So in order to get that letter to Drexel, though, when I want to send the letter to Drexel, I at least have to get it into my mailbox. So in this case, if I want to get a packet from my network to someone else's network, the first thing I need to know is how to get to a router that can then pick it up and route it from there. So the first thing I do is I get my traffic through that switch. I tell the switch, take this packet and somehow get it to my router, which I know is 10.11.12.1. How do I know that? If you look in Windows and you do an IP config, you'll see your default gateway. The default gateway is where that mailbox is that you can put every letter and it can be delivered anywhere in the world. You don't know how it gets there, but you know that that is where you put something where you want it to get outside your network or outside, wherever you are. So the way that works is your computer, since the switch only understands MAC addresses, your computer keeps a small table called an ARP table of a list of all of the MAC addresses, or the IP addresses rather, and a mapping to the MAC address for all the nodes on the network that are directly attached to that switch. So in my computer on 12.13, I have a small table that, along with the switch, or by querying the switch, is able to keep a list of all of the IP addresses and MAC addresses connected to that switch. So that way, when I need to get traffic to my default gateway, my computer simply tells the switch, take this datagram that I'm sending and send it to this MAC address, which I know is the router. So once the router receives that packet, now the router is smart. The router knows that you're trying to get to 172.20.21.22, and it knows that it can send that traffic to a switch connected on port number 2, and at that switch, because it knows the MAC address that it's looking for, it'll deliver that packet downstream. In a complicated network, you'll have more than one router. You'll have many routers, and that datagram is traversing through all these different routers until it gets to another network where it hits a switch, and then finally the destination computer. So that model for how we do routing is really important to understand in networking, in network security devices, because Understanding that routers can pass and block traffic, and understanding that firewalls are sort of like a router on steroids that can pass and drop traffic is an important concept. All right, so back to our OSI model with the TCP model. I talked about the data link layer and the network layer being IP and IC or IP, but another standard we have is ICMP, which allows us to do troubleshooting and so forth. But then we also have TCP, which I'm going to talk about here for just a few minutes, because that's also important to understand for network security. And then UDP, which is sort of a best effort delivery protocol, which I'll talk about very briefly. ICMP is things like ping, path ping, trace route. These are commands that we can use for troubleshooting networks at the network layer without even getting to that transport layer. So we can troubleshoot whether or not our routers are working, our switches are working, and so forth. So that's basically what ICMP is for. And then to support applications like FTP, SSH, Telnet, SNTP, the web, email, and DNS, all these things that we require on our networks, to support that, we use TCP and UDP. So let's just talk very briefly about TCP. If you go and read the RFC that I talked about, TCP basically has 6 goals. The first goal is basic data transfer. So being able to transfer a continuous stream of octets in each direction between its users by packaging some number of octets into segments and transmitting through the internet system. One of the things that's a problem with internet protocol is that it's not reliable. It's not reliable, and it's you have a lot of latency and dropped packets. It's a big shared network, so we can't really rely on it. So TCP is a tool that allows us to make IP more useful. To sort of, we have this very simple, easy to implement protocol in internet protocol that has a lot of disadvantages, but we can mitigate those by using something like TCP, which is layered on top of that. So reliability is the second thing that TCP gives us. It must be able to recover from data that's damaged, lost, duplicated, anything delivered out of order. So we have to make sure it can be put back in the right order to present it to the application, layer. You have flow control, which allows you to control the speed that you're sending data to and from devices so that you can't overwhelm a device. There has to be some mechanism for that flow control. Multiplexing, so that's a fancy way of saying allowing more than one application to use the network at the same time. If you think about your home telephone, for those of you that remember having home telephones, if you're on the phone and somebody else picks up another phone in the house, you hear their conversation, right? So only one person at a time can use the telephone. But if you wanted to resolve that issue, let's say you had a business with multiple phones, you might have extensions so that different people could all be on the phone at the same time. And multiplexing allows that to happen with TCP/IP. Multiplexing allows us to have multiple applications on a single server or computer or client using the network at the same time. And if you think about it, all of you do that on your computer. You'll have the web, you'll have instant messaging, you've got all these different services running in the background that are all using your internet connection. And again, IP does not support that natively. TCP allows us to support that. The other thing is connections. So IP does not have a concept of a dedicated connection between two nodes on the network. So there's no idea of a session that connects two people where you establish some connection. And so that's an important concept. We have to have some way to establish a connection between different devices. And TCP allows us to do that. And then precedence and security, which is very, from an IT security perspective, this is very rudimentary. The security that's baked into TCP, it certainly is not something we can rely on. But what we can rely on in IT security is using all of these other goals in TCP and all the ways the standard supports those things to allow our network security devices to ensure reliability and to use them to control access and control what types of information and datagrams can pass through our networks. And I'll talk briefly about that. But first, just to give you an idea, pragmatically, how does this all work? If I have two computers, let's say I have a computer that's got 16 packets of data or 16 segments of data that I want to deliver to another computer. So that computer, number one, that traffic can arrive through any number of paths because that's how IP networks work. There are routers, and any single packet can get from point A to point B in many different ways. So all these different packets are arriving. Now, every once in a while, some of those packets get lost, but that's okay because once all the packets arrive at the recipient, because of the way TCP works, it allows them to know the order that those packets were received, and they can tell if something is missing. In this case, sequence number 5 is missing. So TCP allows the recipient to go back and say, hey, I never got number 5. Really what happens is the sender never gets an acknowledgement that number 5 was sent, so it realizes that it needs to resend number 5, and now it's there. But one of the other problems in networking is, let's say, the sender is a very powerful computer that can send data very quickly, but my recipient's not as powerful. Well, the sender could overwhelm the recipient by sending too much data where it can't fit into its buffer. So there's some flow control where the recipient can let the sender know, hey, I can't receive the data this fast. You need to slow it down. Here's how fast I can process that data, and that's called windowing. So it allows that to happen. How is all that stuff supported? It's supported through features that are baked into that header in a segment, or the TCP header. We start with a source port and a destination port. That's what allows multiplexing. So having port numbers is what supports multiplexing. The port numbers can be a maximum of 65,535. So for example, a source port could be something like 2791, and I just made that up. A destination port is the port to which you're trying to send on another computer, and you can think of ports almost like an extension in a phone system, where you have the main phone number to get to the company. But once you're inside that building, you've got different extensions to different people that might be listening for a phone call. Just like in our computers, we have our IP address, which gets you to the computer, but then different applications can be using different port numbers, and TCP can handle that. TCP can handle lots of different applications using the network at the same time, and it simply keeps track of who's doing what by using the port numbers. For example, port number 80 is commonly used for things like web servers, although really you can use port numbers for anything. There's nothing that says you can't have some other service using port 80. The sequence number tells the system what sequence that segment was received. And then you also have acknowledgement numbers, which is how you tell that's when you send a message back to the sender to say, here is the sequence number that I received. So they know that you got that sequence number. And if they never get an acknowledgement, they know to resend it, which you saw in my previous graphic. You also have let me get forward here. You also have the flags, which tell you what kind of segment it is. So when a connection is being created, you might have a SYN flag set. When you're acknowledging a connection, you would have the acknowledgement flag set, and so forth. So you can tell the person to whom you're sending the segment exactly what the purposes of the segment is. So that helps support all this stuff. You have a section for the window, which tells you the maximum number of packets they should send. Segments they should send before they wait to receive an acknowledgement. A checksum, which makes sure that that the data has not been adulterated in transit or hasn't been modified in transit. Again, that's not something we can rely on in security because somebody could always just also update the checksum. It's more to make sure that there's not some error in the network that modified some data, which of course happens all the time. Then you got some options and some padding. But again, the important stuff here to understand here is all of these different things support all of those goals of TCP. And in IT security, we want to make sure that our infrastructure supports those goals as well, and that we can leverage all of these things that we see in this header to give us insight as to what's happening with a packet or a segment on our network. We know where it's going, we know where it came from, we know what the purpose is. We can use the sequence numbers and acknowledgement numbers to see if it's an established connection or not, and I'll talk more about that here in just a few minutes. So I talked mostly about the transport layer, the network layer, and the data link layer. The data link layer, the things that we can use in IT security at the data link layer would be things like MAC addresses and the various protocols. So MAC addresses are important. We could, in theory, make it so that only certain MAC addresses can connect to the network as a very simple layer of filtering, for example. At the network layer, At the network layer, we have things like our source IP address, the destination IP address, and which protocol they're using, like IPv4 or IPv6. Again, we can, knowing where the IP traffic is coming from and knowing where it's going to is important. And that's something that we can use in network security. We can use that information to make decisions, or our devices can use that to make decisions as to where we're going to route or if we're going to route traffic into or out of our network. And likewise, at the transport layer, we have our source port, our destination port, the flags, and this concept of the state of a connection between two nodes. And again, we can use all of this in IT security or network security devices. For example, if we know the destination port, we probably know roughly what type of service they're trying to access. We know whether or not to pass that traffic. Now, these things are not all foolproof. We can't always trust the source IP address, for example. Many different types of network attacks, which we talk about in much more detail in IT Security 2. So in IT Security 2, everything I've been talking about, we sort of take it to the next level and we talk about exactly how people utilize, how attackers use all this stuff to carry out attacks to sidestep our network security. But I want you to understand in this course that these are all the things we have available to us, and this is what's being used by routers, switches, firewalls, proxy servers, and even to some extent intrusion detection systems, which we'll talk about in the next unit. But I want you to be aware that all of that is there, and this is all the things that we use. All right, so when you have something like a router or a firewall or a proxy server, they can use rules to evaluate any combination of anything found in all of those headers. And the reason I'm spending so much time talking about those headers is it's pretty much all we have to go on for network traffic. All of our network security devices, no magic sauce here. Everything we have to go on, everything we have to make decisions about what to do with traffic on the network is all derived from those headers and from those standards. There is nothing special, there's nothing fancy that we do here. It's all just information in those headers that we're trying to evaluate to make these decisions. So there's nothing complicated going on here. So whatever we find in that segment TCP header, the packet IP header, or even the frame header, if it's in the local area network. We always have the target and source addresses. We always know the connection state if it's TCP. Again, there's no concept of state in IP, but TCP gives us that ability to know what the state of a connection is. And we can even see the payload or the content. And that's the more complicated thing. So when we talk about proxy servers, when we talk about things like WebSense and email servers and things like that, they may care more about the content. For example, looking at what's in emails to see whether or not we should allow the traffic into our network, or even out of our network, looking at requests to get on the web, looking at what's coming back to a user, if it's appropriate content. Again, we're looking at the actual payload for that. So there are different layers here of protections that we can put in place at these different layers. Most of our network security devices live in that segment, packet, and frame layer. And then we also have the content layer, which is usually things like proxy servers, which are a whole nother category of devices, which your book does talk about those. One of the things the book does talk about that I wanted to make clear exactly what they're talking about here is state. So stateless devices is where we apply a rule to packets, one packet at a time. You can think of stateless as not really having an understanding of anything happening outside looking at that specific packet. So when I think of stateless versus stateful, which I'm going to talk about in a second, a stateless device is sort of like the beat cop on the street at the street corner, whose job is to just look at what's in front of them and evaluate what's in front of them, right? That's all they do. So they look at a car that's going too fast and they cite the car for going too fast. They look at a truck in the wrong lane and they cite the truck for going in the wrong lane. And that's all they do. So their job is to look at what's in front of them. On the other hand, a stateful device understands the connections between devices. It knows what's connected to what. It can look outside the box. It can sort of see a big picture view of what's happening on the network and can make decisions based on that. So a stateful device is more like a detective, where they're not just looking at a single incident, but they can look more deeply into that incident. They can look more. They can expand more. They see the big picture. They're expected to understand a lot more about what's happening to evaluate the situation. So they're a little bit smarter than stateless. Most devices in network security are both stateful and stateless. They understand both. And I'll give you an example of where we care about state. Let's say, if you ask anyone in network security, or if I asked any of you on a test, should we allow traffic from the internet into our network? The answer is mostly no, right? You don't want to let just any traffic into your network. Likewise, let's say you work in an office building. Should we just let anybody into the office? The answer is usually no. Usually, just anybody can't just walk into the office building and go and start walking around the building. They have to stop at the front desk and they have to say, I'm here to see so-and-so. So if somebody comes into Drexel and says, hi, I'm here to see Brian Green. The person at the front desk might say, oh, okay, let me call Brian Green and see if he is expecting you before they just let the person walk to my office, right? Although in reality, a place like Drexel doesn't really do that. It's all pretty open. But let's pretend it's, a formal office building. So they're going to ask for me. And then I'm going to say, yes, I'm expecting that person. They'll allow them through. That's exactly what a stateful device does. A stateful device basically makes sure that when traffic comes in for a certain node, it knows whether or not that device is expecting that traffic. So for example, if I open up my web browser and I go to CNN.com, then I have the expectation that when CNN.com responds to my request for the content at CNN.com, that the router is going to pass, or the firewall is going to pass that information to me and not block it because I asked for it. And that's the example. That is the kind of the textbook definition of what stateful is and why we care about that. Usually when we talk about stateful, you'll see terms like new, established connections, related connections, invalid connections, but you can use the state of a connection to make decisions about what to do with traffic and network security. So from just a kind of a very high level, and your book talks about these different architectures for network security devices, from a very high level, usually you'll have the internet coming into your facility through a firewall. So usually your first line of defense is a firewall that's connected to the internet. And then behind that firewall, you might have public-facing devices like web, FTP servers, and email servers, all of the things that have to interact with things beyond your local area network, or from the internet into your network. But then you'll have another firewall which protects devices that are inside your network that, for the most part, people should not be able to access from outside the network unless we have that established connection that we talked about. This is the sort of conceptual model that most networks use. So usually we divide it into 3 zones. So at a minimum, most network security architectures have the internet zone, what we call the DMZ or the demilitarized zone, and then our internal or trusted zone or our LAN zone. So at a minimum, you'll have these 3 layers. You don't necessarily have to have 2 firewalls. Sometimes one firewall handles all of these different zones. But conceptually, it's essentially like having 2 separate firewalls. You have one that's allowing traffic to the DMZ and another one's that's deciding what traffic gets to the local area network. The idea here is, think back to the office building I talked about. When the traffic comes in from the internet, it's in the vestibule, it's in the lobby. And it can't get into the back area of the office building unless it gets through the lobby. So anyone can kind of walk into the lobby and look around and ask for something, but whether or not they get past that lobby to the inside is another story. So that's kind of how this multi-layer architecture is supposed to work. So again, you'll have your LAN, which is called the trusted side of the connection. You'll have the WAN or untrusted side, your firewall in the middle, which can also allow traffic to a DMZ. Typically, traffic is allowed from a LAN or the trusted to the untrusted. And traffic can usually travel between the DMZ and the LAN and from the WAN to the DMZ. But what you don't see is traffic going directly from the WAN to the LAN. That is never allowed in most network security architectures. We don't have that traffic going directly from one to the other. All right, so just to give you some other examples here, this is another term that you'll talk about in network security and networks in general is things like natting. And basically the way this works is most networks have one or just a few public-facing IP addresses with an unlimited number, practically unlimited number of internal IP addresses. The idea is that we can't give public IP addresses to every device on our networks because we would very quickly run out of IP addresses in the world if we did that. Some organizations still use public IP addresses on everything. Great example is Drexel. To this day, There's a lot of networks at Drexel that have public IP addresses on everything. It's 144 dot something, which is a public IP address. When I went to Drexel in the early noughts in 2000 and whatever, every computer in every dorm had a public IP address. So they were everywhere. But most networks aren't doing that now. Most networks assign their own IP addresses internally, but they have an external IP address that is a public IP address. So you'll have a finite number of IP addresses that face the internet. So, for example, let's say I had a computer in my internal network. I could assign it an IP address that's a public IP of 68.68.68.69. So even though my public IP address is 68, but I might have a computer that needs to be accessible from the internet, I could assign it not only an internal IP address, but also NAT it to a public IP address. And that's network address translation, where we can translate an internal to an external IP address. And likewise, the other computer at the bottom could also have its own IP address. So that's something called network address translation. There's also this thing called port address translation, where we have a single public IP address, but we support multiple ports on that single IP. So maybe all the traffic that's coming in from the internet that's going to port 80 will go to system number 10, and all of the traffic from the internet going to port 25 will go to system number 11. So that's PNATing, or port network address translation. So when traffic comes in for port 80, the firewall is smart enough to know to route that traffic to system number 10, and when it comes in on the public IP address for port 25, it knows to route it to the system listening on port 25. So again, that's network address translation, port network address translation. Some people call this masquerading, and I've even seen the term mangling. But again, this is very common in most networks, and it's important to understand it. So I hope that this presentation gave you at least some background in how networks work. A lot of this maybe have been review for a lot of you, which is fine. For some of you, maybe you haven't seen some of these concepts yet, but as you go through the book and look at these different network security devices like firewalls, routers, proxy servers, I want you to try to put in context to these standards and protocols, put it in context of which of these standards and protocols they use, and try to think about exactly what things in the packet header and the segment header and so forth those devices can use to make the decisions that the book is talking about for network security.